Hello everyone, welcome to my video. In this video, we're looking at example 6/109. One example in work energy relations in general motion equations. We have a system released from rest when the angle was 90 degrees. Determine the angular velocity of the uniform slender when theta equals to 60 degrees. We'll use M1 is 1 kilo, M2 is 1.25 kilograms, and B is 0.4 meters. As I reminded you multiple times in classes, what you want to do is to realize whether this diagram here given to you represent the instant you want to solve. If not, what is the diagram? What does it look like at the instant you want to solve? Or if it is, where is it moving from? What was the initial state? Remember, in physics or in dynamics, you always want to know where do you start with and where do you end up with. So we release from rest with a 90-degree angle. When this angle was 90 degrees, so apparently this is not the initial state. But when we end up with 60 degrees, so it seems like this angle can be 60 degrees. So this is the ending position we want to solve. So where do we start? We start from here, when the angle is 90 degrees. Right, so this is what you want to start with. And then we move, and this slender moved to here because of the weight is pulling it. So in general motion equations, when it comes to moving or solving a process, the number one method should come to you is using work energy equations. Right? What's the initial state? What's the end state? Now, let's call them state number one and state number two. How does energy change from state one to state two? State number one, naturally we'll just set it as the beginning state, which is when theta was 90 degrees. And then we'll arrive at theta equals to 60 degrees. Again, with energy equations, you want to set up your datum. In this case, where do you want to set up your datum? You can set up your datum like right here at this snapshot. When multiple things are moving, especially in this case involving angles, the best practice is to set up a datum using an angle here. Therefore, I would like to set up my datum when the theta was 90 degrees. Okay, so this is what we start with. I'm just still preparing. Also, at the same time, look at this rotation, fixed axis rotation for the slender, uniform slender bar. We will need the mass moment of inertia in the work energy equation. How do you read the mass moment of inertia for the slender bar from the table? So from the table, you can see if it is rotating with respect to this end point of a slender bar, your I can be calculated 1/3 ml squared. And this L is this whole length. Okay, this is read from table. You won't be given those equations. You need to learn how to read those from the table. Okay, so we set up a datum. We recognized we're moving from state number one to state number two. Every state, there are kinetic energy, there are potential energy. And between states, we want to see whether there are any external work done to the system. Okay, so I just mentioned system here. Looking at the system, what do we have? What did we have when theta was 90 degrees? So the M2 will be a bit higher here, and when the bar is vertical, what do we have? We start from rest. At the same time, we define everything or related to potential energy. The potential energy is at its datum, that when potential energy is zero. In this case, we don't have any springs, so the only potential energy is the gravity. So the gravity potential energy when theta was 90 degrees is zero, and because we start from rest, your kinetic energy at the beginning is also zero. So looking at the system level, we start with T1 equals 0 and V1 equals 0. I have seen some of you like to write KE and PE. That's totally fine. I'm just being consistent with the textbook. Now, before we consider what type of energy we end up with in state number 2, think about this. Is there any work done from state 1 to state 2? If yes, what are they? If no, why not? Remember, we're looking at the overall system. So everything, so if I draw a boundary here, this is your boundary. Everything happened within this boundary. Is there any external force applied to this boundary or to this entire system? No. Right? None of them exist. So within the boundary, everything is within the boundaries. Nothing is applied externally. Okay, you may argue, just in case, you may argue, okay, what do we do with this tension here? Right? It seems like the tension is external force. But remember, again, we are looking at the system as a whole. If you have a tension here, then you also have a tension here, right? So this spring or this rope is connecting these two components within the system. The force along the rope is considered internal force. So this is not an external force. So by now, in this case, hopefully you can realize the work done to the system is 0 from 1 to 2. Everything happening in this within the system is the gravitational energy of M2 now dropped, then lifted the bar up from 90 degrees to 60 degrees. Look at the angle here. So that is our half of the equation. State 1, all 0 and no energy done. No work done. What about state number 2? Let's start with kinetic energy. So the bar was vertical, now being pulled. And then we put a pause. At this instant, what kind of energy do we have in terms of kinetic energy? So kinetic energy for translational movement, that is coming from 1/2 mv squared. For rotational movement, that is 1/2 I omega squared. I is mass moment of inertia. Now looking at one at a time. For M2, okay, we'll start with M2 here. M2 was here, right? And then moved to here. Is it translational or rotational? Translational, right? You move upside down, like you moved up and down. So for M2, you start with 0 and you end up with a energy, M2 V2 squared, at this instant when theta equals to 60 degrees. And then for M1, on the other hand, M1 is rotating. For rotational, especially fixed rotational axis motion, our kinetic energy is 1/2 mass moment of inertia omega squared. See how similar these is. Like 1/2 mv squared, 1/2 I omega squared. This is translation. for M2. This is rotation for M1. That's our kinetic part, not potential part. Once again, there's no spring, so the only potential energy is gravitational potential energy. So V2, look at V2 here. Again, we'll start from left to right. M2 was up here and now dropped to here. And we set up a datum when theta was 90 degrees. So our datum would be here, right? And you dropped below datum, your M2 would end up with negative M2G H2. We'll find out H2 in a moment. Don't worry. Okay? But the key thing here is realizing the negative sign here. And then for M1, look at M1. Should M1 has a positive change in potential energy or negative change? And this is when you want to look at where the mass center is. In this case, it's very small. The change is very small. Mass center is here, and when you lift up naturally, like think about if you lift all the way from 90 to 90 degrees, right, your mass center was here, and then all the way up to here. So this will be your distance you raised up. Because M1 was raised up, so a mass center was here probably, and probably end up somewhere here. And our datum is at when theta was 90 degrees. So now in this case, because M1 got raised up, M1 G H1. Okay, we'll find H2 and H1 in a moment. Okay. And then before we proceed, we'll just do the calculation for mass moment of inertia in this case. I naught, as I mentioned at the beginning, 1/2 ml squared. So 3b squared. We'll do the calculation. You know the mass. You know the L, 1.2 squared. 0.48 is your mass moment of inertia. Okay, look at all these equations we have. I naught we solved, right? So it seems like we need to figure out velocity, omega, H2, and H1. Okay, that's our next step. Okay. So we're going to take a look at this. State number 1 and state number 2. When the bar was vertically, right, at vertical, look at A here, okay? A is here, C is here, O is here. Okay, I'm looking at this triangle with a fixed distance B here. This is what's happening. Okay, so this is your triangle AOC at state number 1, and this is your triangle AOC at state number 2. It was 90 degrees, it ended up with 60 degrees. We want to find out how far does the bar lift, right? So given this, first of all, looking at triangle AOC here, we can calculate your AC is Pythagorean theorem, 0.894. This guy here. And when the bar lifted a little bit, it was from vertical position now to a lifted position. This still 0.4. This is 0.8. But you know the angle here. You can use cosine law, right, to find out your A prime C. This is actually very similar to the last question in your midterm. A prime C, in this case, 0.693. Okay, why do I need these two lengths? Now look at the diagram here. It was here, AC is this much. Now it comes to here, A prime C is this much. The difference in this little piece here is actually how far does M2 move, right? M2 dropped that much, right? It's the same, the rope length is the same. So if I take the difference between this AC and A prime C, I can get how far did M2 drop? Minus 0.693. So we have 0.201 meter. Okay, one parameter at a time. So we solve for H2. Okay, H1 is a bit tricky. We'll leave H1 at the end. Now, with this triangle here available, we can utilize the trig geometry to find the relation between length, and then take the derivative of the length to find the relation between velocity. Okay, what does it mean here? Let me start a new section. So if we look at this triangle here, no matter how the thing is moving, right, either from a right angle triangle, either to not like any triangle, your cosine law will always apply. So that means if I write a general equation using cosine law to represent this triangle, I will have, in general, AC squared is always the 4b squared plus b squared minus 2b times b times cos theta. Right? Does it make sense? Because looking at this triangle here, no matter what changes, here to here is always 2b. Here to here is always b. Then this AC will change based on the angle. This 2b won't change. So I'm using a general equation to represent this triangle. How is that going to be helpful in a moment? First of all, let's tidy up a little bit. We'll end up with AC squared equals to, we'll just tidy up here, b squared 5 minus 4 cos theta. Okay, AC is a variable. B is fixed, right? B is the length of the bar. It's a rigid body. The bar won't become longer or shorter. And then theta. Theta is a variable. This is the length. This is theta, angle. What do we want? We wanted the velocity and omega. If we take the derivative of the length, we got velocity. If we take the derivative of theta, we got omega, theta dot, the angular acceleration, right? That's omega. So we'll take the time derivative. Now take time derivative. We'll end up with, on the left-hand side, 2AC. AC is the variable, so we'll have AC dot equals to, on the right-hand side, b squared stays. We have 4b squared. Remember, this is a constant, right? When you multiply here, like b squared 5, during derivative, this part becomes 0. So you only are doing the derivative of 4b squared cos theta prime, right? Take the derivative here. So sine theta times theta dot. Remember, theta is a variable here. Okay, let's tidy up here. Recognize that your AC dot is the same as a velocity 2, right? That's how fast the length, right? The length connecting to the weight number 2, m2 on the left-hand side, right? The length derivative is the velocity of the weight. At the same time, your theta dot is the omega of the bar. So we have 2 times 0.693 V2 equals to 4 times 0.4 squared sine 60 degrees omega. Right? We just need what's happening when theta equals to 60. So tidy up here. V2 equals to 0.4 omega. Okay, great. We got one more relationship, the velocity and omega, right? Which kind of makes sense. You should have a relationship between the velocity, the weight is changing, connects to the omega of the bar. Now that we found H2, V, and omega. The last one is H1. And H1 is depending on where does the mass center move of the bar, right? It was here and then to here. Like how far does it lift? Now for H1, let's take a look. Okay, it was horizontal. Right, horizontal 0.6, 0.6. This is when state number 1 here. Okay, now let me make a copy. Okay, I'll make a copy here. And then I will rotate. Okay, I'll rotate it, and I'll make it match the top point. I'll make them match. Okay, I'm matching here. So I essentially want to find out what is the difference between here. That is how far then my H1 is. So I'm going to find out, make a right angle triangle here. I can calculate. Okay, so this part is 60 degrees. That makes this part is 60 degrees. So this part is 0.6 sine 60 degrees. Okay, do the calculation here. 0.5196 meter. Okay, it was 0.6 from top. Now it is 0.5196 from top, measured from top. Right? As I told you, it's going to be very small. So this, the difference here, representing our H1. How far does the mass center of the slender bar moved up? As we expected, very small, 0.0804 meter. Okay, the difference between 0.6 and 0.6 sine 60. All right, we got everything. H1, H2, V2, omega. And what we want? We wanted omega, right? We wanted the angular velocity of the slender bar. So now let's putting everything here. T1, V1, energy done 1 to 2 equals to T2, V2. We're just now subbing in number here. As we explained at the very beginning, 0, 0, 0. So left-hand side is 0. Right-hand side, 1/2 m2 V2 squared, the kinetic energy of m2, the kinetic energy of m1, the slender bar, minus the potential energy of M2, the weight on the left-hand side, with H2, plus M1 G H1, the potential energy of the slender bar on the right. Right? Let me subbing out the number here so you can follow along. M2, 1.25. V2, omega, 0.4 omega. This is the relationship we got on the previous page. Plus 1/2 I naught, we calculated 0.48 omega squared, that's our unknown we want to solve, minus 9.81. I'm doing some simplification here. I took G to the front, 9.81, inside M2, 1.25 times 0.201 H2 minus 0.0804 times 1, the mass of M1. Then I'll get omega 2, or omega in this case, 2.22 radius per second. This is what's happening when theta equals to 60 degrees. The angular velocity of slender bar, or of this M1 in this case. Okay, I went extra slow with this example. I hope this is clear, and thank you for watching. I'll see you later.